A log is essentially an inverse of an exponential function. Let's write that. Inverse of exponential. Okay, so essentially what this means is that like it kind of solves for an unknown exponent. So for example, if you, okay, so we all know that 2 squared is equal to 4, right? But let's say you didn't know that. Let's say you didn't know what this 2 was. So you would have 2 to the x is equal to 4. And so using logs, you can find out what this x is if you didn't know what it was. So to find out what this x is, you would write it like this. So log, and then the base becomes this number, so 2. And then equals to this would be put here, so that this is equal to x. And now you can put this in your calculator, and that's how you would find it out. I'm not going to do that because I don't want to. Okay, so that's essentially how it works. The general format for a log is log AB is equal to like x or something, right? So what we call this is called the base. This, I don't know, there's a number, but yeah. And this would be like the exponent that you're solving for. Yeah, it would be the exponent of b that you're solving for. And this is just like the base of the exponent, I guess. So this is essentially what your formula will look like. So this base, it can pretty much be anything, but if you come across a question where they don't write it, like they write log b is equal to x, the base over here is just assumed to be 10. So log base 10. Okay, and now you want to convert this to exponential form, right? So like, say you have a logarithm, right? Say you had log 2, 4 is equal to x. Same situation here, right? But this time you want to turn it into the exponential format, which is like y equals a b x, right? Well, I'm using a bunch of different variables here, but you know what I mean. Yeah, so what you would want to do is that this number, oops, what am I doing? Okay, this becomes the, this becomes this, sorry, no, not a b x, just the x. This becomes the a, this becomes the y, and then the x is still the x. So, just remember that. That's a little confusing, I know, the way I described that. Oops, hello? Okay. There we go. That's essentially how it is. So we can bring up some more examples of this. For example, you have 16 is equal to 2 to the 4. How would we rewrite this in log form? Well, you would do log, you put your log down first, right? And then remember how I said the base here becomes the base here, so the 2 gets put down here, right? And now this gets put here, and that's equal to this, your x, which is your 4. And essentially what like this expression is saying is that if this was x, right, it'd say 2 to the what is equal to 16. And well, if you know 2 to the 4 is equal to 16, that's essentially what they're saying. That's essentially what they're asking you. So, yeah. And then, let's try another one. 3 to the negative 2 is equal to 1 over 9. How would you rewrite this? Well, again, right, we are going to take the log here, take this 3, move it down here, take this, put it like here, and then it would be equal to negative 2. So this is saying that 3 to the power of negative 2 will equal to 1 over 9, which is true. And let's try just one final example, where m is equal to n to the 3. How would you rewrite this? There's no numerical values here. Well, you would, same thing, okay, log, right, and then you take the base here, n to the m is equal to this 3 over here. So this means that n to the power of 3 is equal to m, which is pretty cool. Also, it's important to note that you cannot log a negative. So like, this number, oh, whoops, wrong thing, this number, and this number, and this number cannot be a negative. They will always be a positive value. Okay, and now there's some log rules that are very important that you should know. Here, let's title this rules. Great. Okay, some of the most basic ones would be, for example, this isn't really a log rule, this is just like a rule, but say you have x to the a is equal to x to the b, right? Then if two exponents have the same base, you can just ignore them. So it means that a is equal to b. So if you think about it, right, if you have 3 to the y, for example, is equal to 3 to the 4, then y is just equal to 4, because, 3 to the 4 is equal to 3 to the 4. I don't know how much more I can say about that. And then you have log a is equal to 1. So this is saying if your base and your, whatever this is called, is the same value, that will be equal to 1. Because think about it, what they're saying is that what to the power of 1, a to the power of 1 is equal to what? Anything to the power of 1 is just equal to itself, right? So that's how you get that. If you want to put it into a numerical example, for example, if you have log 2 equal to 1, because if you rewrite this in exponential form, you would have 2 to the 1 is equal to 2, which is, correct. Yeah, that's essentially how that goes. And then there's this thing called the power law. It essentially goes like this: log a, b, and if it's raised to an exponent here, so if your term here has like an exponent here, it's just equal, you can move this down over here to become c log a, b. This is just like a rule, I guess. So say you have log 2 to the 2, right? You could make that 2 log 2 to the 2. See what I mean? I moved this over here, and now it's over here. Yeah, and you can see that if you calculate it, it's still correct, because we know that if we solve for the log in here first, right? Whoops. Yeah, log 2 to the 2 is just equal to 2. Sorry, it's equal to 1 because we're applying this rule here, right? This is equal to 1. So you're just multiplying this by 1. Oops, sorry. By 1. And so 2 times 1 is equal to 2. And that would be the same answer here. Because if you could write this one as log 2 to the 4, right? Because 2 squared is equal to 4. And then we know that 2 to the power of 2 is equal to 4. And therefore x is equal to 2. This is equal to x, right? So you get the same answer either way. That's how the power rule essentially works. And then you have the, I don't know what this rule is called, like the sum rule? Or, no, it's called the product rule. Where you have log to the base of a times m times n. Sorry, m times n, yeah. That would be equal to log same base m plus log same base n, right? So you could say you have something that looks like log 2 to the 12, right? And if you don't know what that is, you can separate it. So, okay, let's simplify this time. 12 can be 3 times 4, for example, if this is a situation that's convenient for you. Because these are like nice simple values, right? So you could do log to the 2 to the 3 plus log to 4. And then that just kind of breaks it down for you. And then the next one, similarly, is called the quotient rule. It's basically the same thing, where you have 1 log a to m over n. Like, so you have like something being divided. It becomes log same base m minus log same base n. So yeah, that's if you have log 2 3 over 4 again, for example, it would become log 2 3 minus log 2 4. That's basically it. And then you have this funny rule, I don't know what it's called, but it's essentially saying that log base a b is equal to just b. And keep in mind, this is equal to, this is equal to 1. Yeah, okay. So to prove this, for example, you have y equals log 464. And you want to write this in terms of 4, because, you know, you want this, the base to be the same as you want this to be the same as this. And since we have this, we want to write 64 in terms of 4. So you think to yourself, 4 to the power of what is equal to 64? Well, from your hopefully prior knowledge, you know that log 4, 4 to the 3 is equal to 64. So like these two terms are equivalent. And now that you have the same base, you know that y is just equal to 3. That's pretty nifty. What? Nifty. Handy. I don't know what I'm saying. Yeah. And then, oh yeah, anything logged to the 1 is just equal to 0, because think about it. Anything to the power of 0 is going to be equal to 1. You can have like 3 to the power of 0 and be equal to 1. You can have 10,000 to the power of 0 and be equal to 1. That's essentially how it works. That's not a degree sign, by the way. It kind of looks like that, but it's not. And then, oh yeah, this one we kind of touched on a little bit earlier, but it's like log a to the 1 over n is always equal to negative log a n. Because if you think about it, yes, if you think about it, what am I saying? You know what? I don't want to prove this. I don't feel like proving it. I don't really know how to prove it, but you just have to know this, you know. Also, if you have a to the power of log a m, it's just equal to m for similar reasons as this one. And then, there's also this thing called the change of base rule, where log a b is, if you want to like change your base here, if you want to change this to something a little more convenient, you can do this. So it becomes log c is your new base, the base that you want to change it to, b over log ca, and where c is your desired base. Whoops. Yeah. Okay, so for example, you have log 2 4, and say you really don't like that 2. Okay, you want to change that 2 to something else. You want to change that 2 to 3, for example. So you would write log 3 4 over log 3 2. And now you can have your expression in terms of log 3 instead of log 2. Yeah. Okay, so why don't we try some questions applying these rules? Say you have log 5 6 plus log 5 8 minus log 5 16. Oh, that's really tilted. That's okay. So you can either choose to apply product rule or quotient rule here first. I'm just going to do product rule first because it's the first two terms. So you notice how this has the same base as this. Well, all of them have the same base, but we're looking at this right now. These two have the same base and they're being added together. And if we look at the quotient rule that we put here, right, this is essentially the format that our question is in right now, and we can turn it into this. So we take the log 5 and then multiply our 6 and our 8 together, and that's still log 5 16, right? Oops, equal sign. So now we have log 5 48 minus log 5 16, correct? Yeah. And so now we can apply the quotient rule. So if we look here, we can see that our question right now is in this, is in this format right here. And we want to change it to this to make it simplified. So yeah, it becomes log 5 48 over 16. And if we simplify that down, we just get log 5 3. And this is our answer. Pretty nice. Okay, and now, next situation, we could possibly have log x, right? plus log y plus log 3x minus log y. And, okay, right off the bat, we can kind of eliminate these two because it's plus log y minus log y is the same thing, so we can just exclude that. So now we have log x plus log 3x. Wow, this is pretty great, isn't it? So we can see that we have another situation of the product rule because it's the same base. It's base 10, even though they didn't write it because that's just how they do it. And then you have that. So it becomes log x times 3x. And then you get log 3x squared. Pretty nice. Yeah. And here's one with a little change of base. Okay, we can have log 2 7 over log 2 5 is equal to what? Sorry, I didn't mean to do that. So you could write it as if you look at the change of base rule, right? This is what we have right now. So in this situation, this 2 over here is our C. So it's our new chosen base. Somebody chose that base for us, but we want to convert it back to this here. Okay. So this would be our B and this would be our A. Yeah, A. Over here. So we can just write it in its original form, which was log base 5 7. Isn't that nice? Okay. We don't really have to get more complicated. Oh yeah, this might be also useful to know. There's these things called natural logs. So natural logs, it's essentially log to the base e, where e is Euler's number, and it's just some like constant value that's like 2.14 something or like 2.41 something. I don't know. You don't really have to know it, but log to the base e can be written as ln. So you can find this by on your calculator. It's not that big of a deal. But yeah, essentially when you see ln, it's log to the base of e. So some rules that you might want to know regarding ln is that everything pretty much applies from like the ln rules, except just this one small. Ooh, why are you over there? Okay, this one small thing where log e to the e is just equal to 1. Sorry, ln e is equal to 1 because if ln is log e, and then this gets dropped down. If this is log e to the e, we go back to this rule where log base anything to the same thing is equal to 1. So this is why that is equal to 1. Yeah, this is just so you know, but it doesn't really make a huge part of this. Let's go do some log equations then. Log equations. This is when you're like, you get a bunch of stupid log terms and you have to figure out like the value of x, which is really stupid. So some helpful tips. You always want to start with restrictions, okay? Because oftentimes you'll end up with more than one answer, and then you'll have to eliminate one of them because you can only, unless they ask you for multiple values, you only have one value for x. So start with restrictions. So for example, you know how I said you can't log a negative, right? So typically log a b would be b cannot be greater than 0. How do I? I'm sorry, cannot be less than 0. Yeah, that is a general restriction that you'll have. And then, like another helpful tip is that you want to be in a situation where log a b is equal to c. Like you always want to turn it into this situation because then you can turn it into its exponential form, which is a c equals to b, and this will usually help you find x. So let's do an example of this. Yeah. Say you have log x plus 5, and it's equal to 2 log x minus 1. Yeah. So first you want to set the restrictions. So we know that these cannot be negative, right? Cannot be negative. So so you want to set this equal to 0. X equals negative 5. So this is what x needs to be to make to make this 0. And we can't have anything less than 0. So our restriction for this is that x has to be greater than negative 5. And for this one, similar. X equals 1. Sorry, x minus 1 equals 0, so x equals 1. And that means x has to be greater than 1. Those are just your restrictions. Okay. So, when you get to this part, you can now start solving. So, since we have these two terms, first what we want to do is we want to move this over here. We want to make it back to its exponent using the product rule. So, you can rewrite this as log x plus 5 is equal to log x minus 1 squared. And now that you just have your logs here, you can cancel them out because, look, here. Wait, no, it's not a rule. But usually when two sides are being logged, you can just, like, ignore this. So now you're stuck with x plus 5 is equal to x minus 1. Whoops. X minus 1 squared. Right? And then you can expand this to become x squared minus 2x plus 1. Yeah. And then you want to, make everything equal to 0. So then you end up with x squared minus 3x minus 4 equals 0 once you, add over there. Okay. And now you can factor this. So you want to find something that adds to negative 3 and multiplies to negative 4. What could that possibly be? Well, negative 4 and positive 1. So now you have x minus 4 and x plus 1 is equal to 0. So your roots could possibly be x is equal to 4 or x is equal to, negative 1. And looking at this, right, we see that x has to be greater than positive 1. So that means this is not possible because this is less than positive 1. So that means our answer is x is equal to 4. Let's just write that down. So that means x is equal to 4. This is our final solution. We can try another one. Yeah. So for example, you have log base 5, 2x minus 3, and you have that equals to 2, right? So if you apply this is like what I'm talking about. This is in the form of this. So you want to turn it into its exponential form. So remember, this base over here, this 5, becomes the base of your exponent. This becomes here, right? Equals to 2x minus 3. And we know that 5 squared is equal to 25. So we just put that here. And now we want to solve, okay? So 25, if you add 3 to both sides, then 2x will eventually be equal to 28. And then now you're dividing 2 on both sides, so it becomes x is equal to 14. That's not too bad, right? Yeah, no. Now let's do some derivatives of logs. Oh, my back hurts. Okay. Derivatives of logs. Okay, so log, some rules of the derivatives that you should know, that log bx is equal to 1 over x ln b. I don't really know why, but yeah. It's also important to mention this is not a function, okay? This is just like a value. This is a variable for a value. If your x value is a function, then it's different. You have to apply the chain rule, which we talked about before, I believe. So log b of a function is 1 over, same rule applied here, okay? F of x ln b. But you also have to multiply it by the derivative of f of x because this is chain rule. Okay? Easy enough? Yes. And now some rules for natural logs. The derivative of ln x is equal to 1 over x, simply. The derivative of ln, say there's a variable before your x, it's still just 1x. And then, so like, essentially, if, for example, this might be ln x minus 2, ln 2x, it's still just 1 over x. Easy. And then, here, if you have ln x to an exponent, it'll just be the exponent over x. So if you had ln x squared, it'd be 2 over x. And if you have ln u, it would just be equal to the derivative of u over u. Yeah. This is like a little similar to this one, but this one is essentially just saying that like the derivative of x is equal to 1. That's why there's a 1 there. But if it wasn't just x, it'd be the derivative. And then if you have log base a u, it'll be equal to the derivative of u over u times 1a. Similar, very similar. Okay, so let's do some practice questions. Yeah. Say you have 2 ln 1 plus x squared. So immediately we can see that this is the ln of a function. Like this, right? So we know that we have to apply chain rule here. So what we want to do first is, also this is basically just equivalent to log e 1 plus x squared, by the way. So we want to put it in this form. So we have 2, we can keep the 2 outside, and then we have 1 over 1 plus x squared ln e. And then what is the derivative of the inside function? Well, it's just 2x. So you have that. So you can multiply these together, and it'll give you 4x times 1 over 1 plus x squared. And this can be excluded because this is just 1. Log e to the e is just 1. So your final answer would be 4x over 1 plus x squared. That is your derivative. And an alternative for this solution is if you wanted to use ln rules instead of log rules, you could just write it like this. So you know how ln x is equal to 1 over x? Well, then you have 2 ln 1 plus x squared, right? This is essentially x. So you can just write 2 times 1 over 1 plus x squared. And then chain rule it, of course, because it's a function, so times it by 2. You still get 4x over 1 plus x squared. So it's the same thing, it's just faster. Yeah, and then we can go here. It's a very similar thing. Where you just have 2 log 3x squared. And that is equal to, oops, wrong color. That is equal to 2 times 1 over, remember the function, so 3x squared, 110, right, because this is base 10, times the derivative of this, which is 6x. And then you land with 12x over 3x squared ln 10, which you can divide this as 4 over x ln 10. And that is your final answer, which is very fun.